sixth lecture of the first module of the Principles of Oceanography. So bathymetry, if you've never heard the word before, is the study of the depths of the ocean and what the seafloor looks like. So bathymetry encompasses both. So how deep is the ocean and what's down there? Is it flat and just muddy, or is there actually stuff? And that's where the topography component comes in. Bathymetry is studied in a number of ways, and we'll talk about a handful of them and how they've changed over time, starting with fairly simple things like echo sounding and moving towards satellites as bathymetric tools. Most of the interesting features of the ocean floor are generated by plate tectonics and the fact that the crust is moving and these different plates are moving. And so it means that the seafloor has really interesting features, much like the land does. And the features of the seafloor are very different depending on where you are in the ocean. And this is something that's really only been known, I would say, the past 50 or 60 years. So bathymetry measures the vertical distance from the ocean's surface to the seafloor, which includes mountains, valleys, plains, volcanoes, and all sorts of features. Originally, the soundings were the way that the depth of the ocean and the various features were discovered. So this is when you go out on a boat and you bring with you a really, 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 really long piece of rope, and you stick a heavy weight on the end of it, and you drop it and basically see how far it goes. So measure how much rope or line you need. This was kind of the best there was for a good 2,000 years. This was actually started with the peoples living in northern Africa. And the way that they would measure the distance was a fathom. And you might have heard this before as an old oceanography term. And this was a unit of measure. So what it basically means is you take a rope and you stretch your arms as long as you can. So basically your wingspan. And as you pull the rope up, you do that. You count how many of your wingspan it covers. And that's roughly, for the average dude who was on a boat back then, was roughly about 6 feet. So a fathom as a unit of measure is roughly the average wingspan of an adult male, which is roughly 1.8 meters. Not super useful in modern times, but for a very long time it was what was used. The HMS Challenger, which you are probably used to thinking of as Darwin's ship, also made sounding measurements fairly systematically the whole time that it was cruising. And that was really where the idea that there's relief on the ocean floor, so that there's variations in the depth of the seafloor, meaning that there's features, right? That it's not just completely flat. After that, echo soundings were used. So this was a big advance in discovering that you could use sound to measure the seafloor. So you could have a ship that would let out a sound, so make a loud noise, and then wait and measure how long it took for that sound to come back. If the ocean is deeper, it's going to take longer for the sound to come back. And thankfully, the speed of sound is fairly constant. This really took off in the 1920s and thereafter, because what was discovered was that if the sound hit a submarine, it would bounce back in a faster and relatively easy to identify way. And so, of course, during the World Wars, when submarine warfare became a thing, governments pumped a lot of money into figuring out how to use this as a way to spot subs. But it ended up, as a result of World War II, and all of this time spent looking for submarines was also time spent basically mapping the seafloor. And so, as in many ways, the war led to a big scientific advance. It's still not perfect. It lacks detail, and so it can be a little bit inaccurate, but it was a big advance from the previous way of just dropping rope. This is an example of an old echo sounder, what you would get. It's actually surprisingly detailed. So you've got your continental shelf here, so looking offshore. And what you're doing is they're sending the noise back, and it's creating this, allowing them to create this line. So they can see the continental shelf, and then it gets deeper into the continental slope, and then there's some interesting features, and then it goes all the way down. This here, also, you can see the sound is bumping off of something, and this is at just about 400 meters. And this is highlighting that you can also use sound to identify a really high concentration of marine organisms. So this is probably a bunch of phytoplankton and zooplankton and all sorts of stuff, creating this bounce back here, which is also kind of cool that they can use that. Okay, next up, and again, this is as a result of war technology, came the precision depth recorder. So this was about the 1950s, and it was still sound, but in this case, it was a focused high-frequency sound beam. So this was something that was developed intentionally to measure the seafloor. And this is where you started to get somewhat reliable maps of the seafloor. And it was a really big deal in terms of proving plate tectonics. Because one of the things with plate tectonics was that in order for it to be true, you had to have basically a big rip in the earth somewhere where the plates were moving away from one another. And nobody had really, and this would have had to be true in the ocean, and people didn't really think that this was possible. But precision depth recording helped prove that in fact the seafloor is spreading, which was a really important piece of evidence for plate tectonics. And this map here, this is one of Marie Tharp's maps. I hope you guys have all seen that little video that I posted on Vula. And she drew this by hand based on all those PDR readings and confirmed the biggest thing was that this mid-ocean ridge went all the way down. And this really clinched plate tectonics. And I don't know if the video talks about it explicitly or not, but they made her redraw this map more than once because nobody believed that there could be a feature like the Mid-Atlantic Ridge cutting all the way through. But it's a pretty cool map. Okay, moving to modern times. Ships started being able to use what they call multi-beam echo sounders. So this was now multiple sound frequencies, and you can see then it allowed for a sort of wider swath of the seafloor to be explored. And the C-beam was the name of the first multi-beam echo sounder. So this would give you a strip about 60 kilometers wide. And what the ship would do is it would do what they call the lawnmower. So just go back and forth over a region, and then you could stitch these 60 kilometer wide things together to get an idea of what the seafloor looks like. But already just looking at this, you can see how much more detail there is, you know, in this kind of sounding, or this kind of an approach as compared to the sounding. And then we moved on to sonar, which stands for sound navigation and ranging. And sonar can be really useful, especially side scan sonar. So what would happen, so the problem with this approach here is that in really deep waters, this would start to spread out in a way that that became not useful. And so this side scan sonar, what's cool about this is a submersible that you can lower closer to the seafloor. This shows here that's 50 meters depth, but you can even lower it even further. And then you tow it behind the ship, and it puts these sonar out to the sides, and it gives you this sort of split view. So now you can see this image is getting really detailed. Of course, where there's a gap in the middle where the actual submersible is traveling. But you can start to get quite detailed images here. And this is a real side scan sonar image of a volcano in the Pacific, and you can see the crater of the volcano here. And then the most recent approach is to use satellites, which sort of seems crazy, right? How are satellites seeing all the way to the seafloor? But it actually works really well. So when you have a feature on the seafloor, it creates gravitational bulges in the sea surface. And so by measuring the sea surface and the anomalies, it indirectly reveals the bathymetry. And so the satellite isn't directly measuring the sea floor, the satellite is measuring the sea surface and these small changes in the sea surface that result from changes in the topography of the sea floor. And these can give you way more detailed maps. So on the left is a bathymetry map of a part of the ocean using ships and echo sounders and seamounts and things. And you can see each of these blue lines is a ship track. And it's doing a pretty good job of giving you the bathymetry, but on the right you have a satellite image of the same thing. And you can see it's giving you a lot more detail in the features here using the satellite as compared to using the ships. And of course, ships are limited in where they can go and how often, whereas the satellites give you a whole Earth view all at once. So this is the seafloor mapping from space is what's relied on now. And this is from measuring the ocean surface gravity relationships. And And what we do is, or what's done is, the places where we have depth soundings are used to calibrate and make sure the satellites are doing a good job. And so it keeps the satellites honest in places where we have both ship-based measurements and satellites. So here, this is a fairly recent map of the seafloor using satellite data. And so what you're seeing here is the continents have all been blacked out. And here is sort of a focused look at the Pacific and the Indian. And what you have in the bottom charts are these what are called gravity anomalies. And so it's measuring these anomalies. So really deep parts of the ocean are in the purples and blues. So like your deep ocean trenches. And you can see a couple of these here. On the west coast of South America, you've got a deep ocean trench. That's because there's an oceanic plate subducting underneath a continental plate. And then the higher regions, like your undersea mountains, are in your reds and oranges. And so here you can see, for example, if we move over to the Atlantic, you've got the Mid-Atlantic Ridge in orange here, because this is actually a mountain feature. And you can see other parts of the ocean that have, there's actually quite a few mountainous features. So this is pretty cool. And then this is more than just bathymetry, just to give you guys an example. So you can also use noise to not just look at what the seafloor is doing, but actually to penetrate into the seafloor. So this is sort of getting into real geology, where you're looking at the various rock layers. And this is done a lot in, for example, like oil and gas exploration. This is another example of that. Okay, but moving on. So that's how we measure bathymetry and topography, but then how do we actually classify it? You know, what names do we give? What are the major features? And if we think about the seafloor, we can break it down into the continental margins, which are the shallower areas close to shore, the deep ocean basins, so these are your sort of middle of the seafloor, you know, where it's deepest, and then the mid-ocean ridges, which are these submarine mountain ranges. Those are sort of the three big features of the seafloor topography. And so this is interesting. This is a way of looking at a cross-section from the seafloor. So, and you guys have to do this for your practical. So if you start at point A here, which is in Canada, and you literally walk into the sea, and you walk along the bottom of the sea all the way until you hit Africa, what would your journey look like? And so another way to look at that is to go up here and see, like, all right, so you're standing on the beach. This is you. You can see I'm an excellent artist. And you walk down across the continental margin, so the continental shelf, and then it gets deeper and deeper, and now you're walking across this deep ocean basin. It's pretty flat, it's pretty deep. And then you start walking up a mountain, which is basically the mid-ocean ridge. So now you're like here, and then you're going down the mountain, and you've gone up and down this mountain range, and now you're in the other deep ocean basin. And then you start to walk up onto the beach, which takes a long time, and you come up on this continental margin here. So it's a way of sort of visually looking 3D of what you would expect to see as you go across, in this case, the North Atlantic. And these continental margins, so there's one, sort of here, and then the continental margin here, denoted on this part. They can be passive or active. And so what that means is it depends on what's happening with the plates and with the plate tectonics. So a passive continental margin means there's not much happening. There's no exciting movement. There's no major tectonic activity, meaning there's no volcanic activity and stuff like that. The example the textbook, of course, gives is the East Coast of the United States, because it's an American textbook. And the opposite of this would be an active continental margin. And so this is when you do have plates moving and there's a lot of tectonic activity. And this figure, I think, is really nice, sort of highlighting the difference. So on the left here is a passive continental margin, where you've got a fairly big continental shelf, and then it starts to slope down, and you've got a little continental rise, and then basically you've got this massive, just flat ocean until you hit the mid-ocean ridge. On the right over here is an active continental margin, and you can see the difference here is you've got this oceanic plate subducting down underneath this continental plate. And so where you've got these plates bumping into each other, it creates a deep trench, and you've got a much smaller continental shelf as compared to the passive side, and then a bit of a steeper continental slope. You also, because of the movement of the plates, will frequently have seamounts, which are underwater volcanoes. And they're more typically associated with active continental margins. You won't see any underwater volcanoes over here. Okay, so to summarize, active continental margins are where you've got convergent plate boundaries, so plates bumping into each other. You frequently have volcanoes, you have a narrow shelf, you'll have some sort of an offshore trench, and this is true of, for example, the Western South America. If you go back and look at that map of the, well, let's just go back and look. So Western South America, you see this dark blue line? That's the trench that results from the plates bumping into each other. Okay. There's also this additional type of continental margin. Don't worry about it too much, but suffice it to say, also active, but slightly different. Okay, so the continental margin features are the continental shelf, and then you have the shelf break, and then your continental slope and your continental rise. Here, this is again another blow up of this. So your continental shelf is this nice flat, so you're on the beach here, it's quite far out, you can't see it, but it's this relatively shallow area until you hit the shelf break where it sort of falls off into the deeper ocean. And so the shelf break is this sort of line here, and then this continental slope is this part here, off into the deep ocean. This is actually really, countries care a lot about this because the width of the continental shelf sort of controls where a country's own land ends versus where you hit like international waters. So there's a lot of reasons people study this, these continental shelves. They can be really important economically. So the continental shelf is that flat zone from the shore to the shelf break where everything starts to slope. And this is what I was saying. So geologically, it's considered part of the continent. And so from a country's perspective, you want your continental shelf to be as big as possible, particularly if there's things like minerals or useful things there. On average, a continental shelf is about 70 kilometers. Some of them are really big, can be up to 1,500 kilometers. And the waters there are not that deep, about 135 meters on average. This is the west coast of the US, and whether your continental shelf is passive or active or transform sort of controls what your shelf looks like. So this part of the ocean is very geologically active. So there's big fault plates here, and so that's why you can see there's a lot of texture to the seafloor on this coast. There's all sorts of mountains and basins and all kinds of stuff happening, and that's because it's one of these really active continental margins. So the continental slope is where technically the deep ocean starts to begin. It's a little bit like a mountain range, like going down the side of a mountain. Can be quite steep, depends on where you are. Can be 1 degree gradient, but can be up to a 25 degree gradient. And a feature of the continental slope are these submarine canyons. Okay, so the mid-ocean ridge is another dominant feature of the seafloor. So the mid-ocean ridge is these massive mountain chains in the middle of the ocean floor. On average, about 2.5 kilometers above the surrounding seafloor, so pretty good size. Some of them can be volcanic. You can have lava, and these mid-ocean ridges are basically where the plates are moving away from one another. So it's like a ripping of the seafloor. This is a view of the Mid-Atlantic Ridge cutting through the North Atlantic. So you've got your continental shelf, you cut down this continental slope, your deep ocean plains, and then you start going up the mountain again here on the Mid-Atlantic Ridge. Cool. So the mid-ocean ridge features can have rift valleys, much like on land. So these crests and fissures and faults and small earthquakes and all sorts of tectonic activity. A seamount is something that occurs near the mid-ocean ridge, and that's what you can see here in this topographic map. It's basically a volcano, a volcanic seamount. And you can have all sorts of lava. So this is pillow lava in this middle photo. That's an actual photo. And this is, again, an actual photo. So this is lava that comes out, just like lava out of a volcano, except instead of hitting the air, it hits the really cold, deep ocean. And so it cools really quickly. And this is, on the right, this picture C is what this pillow lava looks like once it's been uplifted onto land. So this is now an on-land feature that used to be at the bottom of the ocean. The other super, super cool feature of the mid-ocean ridge are hydrothermal vents. And I posted a short little 3-minute video about hydrothermal vents that you guys should watch. It's actual footage from a vent. They're really cool. Super deep, seafloor hot springs. They have a completely unique ecosystem that survives without sunlight, which scientists for the longest time thought that was completely impossible. But it turns out it's true, and it's happening all over the seafloor. There's warm water vents, which are sort of not very exciting, but then these white smokers and these black smokers are emitting water that's above 350 degrees C, so insanely hot water, filled with all sorts of minerals and stuff from the deep within the earth. And so what happens is basically you end up with this seawater seeps down and mixes with the magma deep in, and then they start to pressure causes them to spew out, and they're called these black smokers. And that's actually what they look like in the middle here. They look like it's just spewing this black smoke. And it results in these massive chimneys, 3 meters tall chimneys on the seafloor. And again, you should watch the video. It's really cool. It's really interesting. Okay, so that's it for hydrothermal vents. We will move on. This is only going to be a 1 lecture series on bathymetry, but later we will talk about